I believe that I am live. Connection. Yes, I think the internet connection is fine now. Yeah, so the frames dropped are of course 0. Let's get started. This is our topic. Digit dynamic programming. Just give me a moment. Let me just refresh this. Yeah, this should work now. Yeah. Okay, so what is digit dynamic programming and why do we need this? For example, let's say you are given a question that count the number of integers from 1 to 500 whose digit sum is 7. So I want to count how many, like for example 7 will work, 43 will work, 34 will work, because the digit sum of these numbers is equal to 7. The one way is to brute force it. I can just say that let's go from 1, or let's just say 4. I can just say that I go from 1 to 500, and then using a while inside I can do a digit extraction and count and see if the digit sum is equal to 7. If it is, then I can have a count variable outside and say that okay, then if digit sum is 7, let the count be incremented, and in the end we can result. In the end we can give the result. Now this is possible, but this will only work if n is up to 10 to the power 5 or 10 to the power 6 highest. Why? Because this is an order n solution. Of course, digit extraction is log base 10 of that. So maximum n times log base 10 n, or n log n solution, like going through every digit one by one, and extraction of digit is log n base 10, because think about how many times I can reduce or divide it by 10 until it reaches 0. That is log base 10 of that number now. So this is an order n solution. Now in digit dynamic programming, we try to approach these problems with a different mindset. The different mindset being, what if we do not want to loop through the numbers? What if we just want to iterate over the digits and like let's say this is a big number, 1 5 7 3 2 1 4 6 6 6 3 8. Let's say this is a very big number. I want to formulate my solution based on these digits iteration, not actually incrementing one by one, going through every number specifically. We want to put digits and play with the digits. Like here I will try to put 0 up to 9, here 0 up to 9. I will try, and I will check out of these which are less than or equal to my target, I will try to count those indirectly through recursive and then maybe memoization. So I will try to put digits, like if you have studied the n-queens problem, you see that in a specific area of a board I try to place a queen, and maybe based on that I go over the board and solve problems and try to restrict that, put some conditions if it is attacking or not. Similarly here also, at every position we will try to put some digit and check if it gets us to a viable solution or not. So this is the idea of digit dynamic programming. So this kind of helps us solve this entire thing in order of, so digit DP solves these problems in order of number of digits, approximately, not exactly, but approximately number of digits. So if it is number of digits now, I can go up to number of digits equal to 10 to the power 5. So n I can now restrict it to 10 to the power 10 to the power 5. Up to this we can possibly solve these kinds of problems. Of course there are small restrictions, but this is the, you can say, the power of using the digit dynamic programming. So like any value which is around 10 to the power 8 or 10 to the power 9 or 10 to the power 12, that cannot be solved in order n. Okay, now let me give you one example of such problem. Just give me a moment, let me find a problem for you. Yeah. This problem. Like consider this problem. Yeah. Consider this problem, number of digit 1. So here we want to count the total number of ones that appear in this series of numbers, which is up to 10 to the power 9. Of course we cannot loop through, we have to go through every digit or every number indirectly and count how many times the digit 1 has appeared. So that is our first clue. Whenever we are discussing digits or trying to do some calculation based on some idea revolving around digits, that is the first hint to maybe we can apply digit dynamic programming. Yeah, so this is the first problem we will probably try to solve. Now there are some concepts that we need to know in order to approach a digit DP problem. First, let's try to understand. So of course we know that in a dynamic programming we have something called a state and we have something called transition. The states will be indices, value of type leading 0, sum of digits, number of times 1, number of times a particular digit, maybe create a map, create a mask, that sort of thing. Let's go over them one by one. So let's say this is a number. So of course we will go through them digit by digit. So we will need something called an index. This will be one state, very important step for dynamic for digit DB. Next thing, say I want to know how many numbers less than equal to 346. Now of course we can put 3 digits, but if I put 4 here, then this will exceed my target. So we will keep track of these boundaries by using a variable called tight. I will explain what tight is. Initially my tight is 1 and I go over to this digit. Now here I will try putting digit by digit. Now the upper bound of this digit is decided by the tight. Tight is a boolean variable. Now initially the tight is 1. That means if tight is 1, the upper bound is defined by this thing. So the upper bound here is 3. So I can put 0, 1, 2 or 3, not more. Now let's say if I put 2 here, then if I put 2 here, the tight for the next index will be 0, because I do not care what I put here, even 9 if I had put 2 here. But if I had put 3, then the tight for the next index will be 1, because that next index will be limited by this 4. So tight tells me, am I limited by this digit in this position? Like on the ith index, I want to know if I am limited by the actual number less than equal to I am trying to form. So let's say I put 2 here, let's say I put 3 here, and then I put a 1 here. If I put a 1 here, that means the tight for the next one will be 0. I can put any value. So the tight is dependent on what value of tight I came with and what I am putting on this position. If I came with a value of tight equal to 0, automatically the tight for every rest of the people will be 0, because that is already less. Like on the left side it is already less, so I have freedom to put any digit from 0 to 9. But if I came with a tight 1, then my digit that I will put on this index will be limited, and if I put the maximum digit on my current position, the tight for the next will be 1, otherwise the tight for the next will be 0. I hope this is understandable. So this is the concept of tight in a digit dynamic programming. Next concept that we will discuss is called leading 0. Of course, we will not require this concept in every question, but these are the basic things that we require to handle. Okay. Now let's say my upper bound up to which I want to check through some loop is 49377. So, and let's say I want to count how many times 0 has appeared in the number. Now try to understand. Let's say I have started forming a number and I put a 0 and here 0 and a 0 and then a 3 and a 3. Possible. But if I do normal calculation, then these 0 will also be counted as number of zeros. But if you consider this number in real life, do we consider these as important zeros, as zeros that have appeared in this number? No. So we will keep track. Initially the value of leading 0 will be 1, and the moment a non-zero value comes, I will make the leading 0 variable equal to 0. So initially LZ equal to 1, and as long as LZ is 1, we will not consider any zeros in our calculation. The moment I find a value that is not equal to 0, I will set leading 0. Sorry, initially the leading 0 is 1. Yeah. The moment I find something that is non-zero, so I should write the moment I set my LZ value to be 0. Now if my LZ value is 0, that means I have to consider the zeros if it comes as we put in the digits. I hope this is clear. Okay. This should be enough. Now let's try to solve some problems. Okay, so this is the first problem that we want to solve. So given an integer n, I want to count the total number of times 1 has come without looping through every number. Okay, so let me give you a framework on how we can solve these kinds of problems, and then we will write down the code. First, try to understand that I will form a set and I will go digit by digit, put in digits, and moment I find 1, of course I have to keep track of if 1 has appeared, and maybe the count of that we have to keep track of. Okay, so let me define the recursive function. The return type is integer, so which will count the number of stuff. I think they have not mentioned any modulo thingy, and the return type is int, so our answer is expected to be fitted into a simple integer. So let's say solve. First index is always the first state variable is the index. So 0, 1, 2, the digits that will form. Second thing is called the type. Third thing is called leading 0, even though in this problem leading 0 maintenance is not required, but we are doing it anyways. And I think we have to keep track of the count of 1, so let's call it C1. And while we are solving digit DB problems, we will consider every number as a string so that we can go through them one by one, character by character. Okay, so const string. Why constant? Because we will not be modifying this. We will just use this. Like for example, if this n is let's say 10 to the power 8, then our string is 10 to the power 8 consistent. We will just put values and check, and index we will check. We will be not be modifying this at all. This is just the upper bound. You can not use the const word as well, but I recommend using it to save memory. So we can call it the S, or you can say upper bound. Okay, so I just call it S. Okay, this will be used to, understand the limit of every particular index. First is the base case, that if idx, if I have reached the end, maybe I should return the count of the one. Otherwise, I will define my upper bound based on my tight. So int lower bound equal to 0 and int upper bound equal to, I will ask, is tight equal to 1, or since it's bool we don't care. So if tight, then I will say it should be s of idx minus 0 to convert it to integer, otherwise it is 9. Now we will put digit, not technically put, assume to put. So int, so let's start from lower bound and go up to the upper bound, and we will maybe count the 1. So let's define my result to be 0. So I will put digit one by one, and I will get the digit from the next sections or next indices and all recursively. Then we will memoize it in the end. What I will say is result, let's get the result from the same solve function. The idx will be incremented. Tight will depend on, am I already tight, and is this I is equal to upper bound, then the next value of tight will be that. Leading 0 will be defined by, it has to be, previously the leading 0 has to be true, and this I has to be equal to 0, then only, or the digit has to be equal to 0, and the count of 1 will be C1, that is currently we have, plus if this digit is 1, and the S will go as it is. Okay, now in the end just return the result. So this is the way of getting answer from all the next positions. Okay. I can just get rid of this bracket to clean up the code maybe a little bit. Now this was the base case and all. Yeah, now we will go and say that we want to return this solve function. Initially the value of idx is 0, tight is 1, leading 0 is also 1, count is 0, and the string s is, since we are given an integer, we can use the toString function. Let's try to run if we have some to check for how about I put an AND here. Okay, but this will probably give time limit exceeded because we have just used recursion and not memoization. So let's try to submit and we'll probably get TLE. Yeah, time limit exceeded. 35 out of 38 cases have passed. Now we will try to memoize this. extremely simple memoization. We will just see what ranges are used where. So let's make a DP array. For index, I think it is the maximum index is 9 indices, because 9 maximum digits I can have. But so the maximum number is 10 followed by 9 digits, 9 zeros. So maximum 10 digits we can have. So 10. Value of type can be 0 or 1, so 2 is enough. Same goes for LZ, 0 or 1. C1, count of 1. Imagine all the 10 digits are 1. So maximum 10. And that is enough. Now before just going, we just check that if dp of this idx type lz I'm thinking that the value of c1 can be 0 as well. The value of c1 can be 10 as well. So 0 up to 10 we need to. So I guess 11 will be a good. Because if I have 10 digits, but I am doing 0 based indexing now, I think 10 is sufficient. But the count can be from 0 up to 10. Yeah, for this 10 is sufficient. But for count, I don't think the dp of here, I need the access of 10, because 10 digits are possible now. Yeah. But index will maximum be 9. Right? 0 up to 9. So 10 size is sufficient. Okay. So, and C1, and then, so I will say that if this is not calculated, then just return this. And before returning the result, I will just say this equal to result. So before calculation, I have to say, let's initialize by using memset. So dp let's try to run. Yeah, it will be just be not equal to. It's giving wrong answer. Oh, it will be -1. Okay, yeah, I gave equal to by mistake. I can remove the comment. Let's try to submit. Okay, this gets accepted. I hope the solution is clear. Probably we could have done this without the leading zero, but maintaining this is never, I should say, a problem. Okay, you can maintain this. How did I understand that leading zero might not be important? Because here you are counting the number of ones, so no way my answer is dependent on leading zeros, right? But try to understand, if this same question had asked, count the total number of zeros in all the digits that appear in this range, then I would have to keep track. So before writing c1 plus I equal to 0, I would have to consider that if leading zero is 1 or not. And that will be all for this question. Now we will go on to the next problem there. Let's see what next problem we have. This is the next problem that we are going to solve. This problem is called classy numbers. Let's try to understand what this problem tries to say. So I'm also solving this for the first time. If you see that I have not submitted any solution to this problem yet. So let's call some positive integer classy if its decimal representation contains no more than 3 non-zero digits. So no more than, so at the most 3 non-zero digits, right? So for example, the number 4 has 1 non-zero digit. Good. 200,000, same, 1 non-zero digit. 1210203, 3 non-zero digits. Will be classy. 4231 will not be classy because 4 non-zero digits, and so on. Now I think we are given a range and we have to calculate how many classy numbers are in this range. Very simple problem. Okay. So I will try to write down a solution to this. So maybe let's go to submit code, C, and we will write it here only. Okay. A better way to do this will be probably in some code editor. Let me see if I can share that. Yeah. Can I make this full screen? I think I cannot make this full screen yet, but let's see if I can make this visible. But just give me a moment. Yeah, this should work. One thing that this is just a template. Let me just use the basic one. So I have not done much. I've just included this is just some comment. Okay, so I've just included bits.std++. Just give me a moment, just let me fix this small error. Yeah, so let's try to code it. Can I do full screen? Yeah. Okay, so we have two integers, L and R. So, and I think the L and R can be up to, let's go to the problem. Up to 10 to the power 80. So it has to be taken in long or string, right? So let's take them as string. Of course, we have to consider test cases. So let's say int t and now here we will use one concept that is called, this is probably known to you from the idea of prefix sum. In digit DP now we don't actually have the control over ranges. So what we do now, we consider the answer from 0 up to some number, and then we subtract from 0 to L minus 1. So 0 to R we calculate, and 0 to L minus 1 we calculate, and from 0 to R the answer, we subtract the answer of 0 to L minus 1. So you may know this from the prefix sum idea if you have done so. I'm sure you have done because you are watching a lecture on digit DP. So it's like, let me just write this for you, just to be, for example, like remember that if I had an array and I wanted to calculate the sum from this L to this R, what we used to do, we used to calculate the sum from 0 to R and we used to subtract the sum of 0 to L minus 1. So if I subtract this now, you see I'm getting the sum of L to R. This is the overlapping range. I hope this is clear. So this idea we are using. So we will calculate the sum from 0 to R and we will subtract the sum. So we will be using the digit DP function twice. Okay. So let's make the function, I guess. So the answer can be very large or small. Let's check. Do I have requirement of any modulo? No, I don't see any modulo thingy. I think the answer will easily fit in a long integer at least. So let's try. So if if they have not mentioned that the number can be very large, then it's not really required to do any modulo thingy. But it's a very common thing that in DGTP solutions the answer can get very large. So every time we are adding to the result, we just do a modulo. Extremely simple thing. If you have worked with modulo, even if in very simple sums, this is just one extra step. Nothing out of the ordinary. Okay, so of course we will memoize it later. So maybe LL solve. LL is long now. We have defined. First thing is the index, which is up to 18 maximum. I think 19. 18 possible, 10 to the power 18, so 10 followed by 18 digits. I mean 1 followed by 18 zeros. So 19 total positions I need to take care of. Yeah, 19 size will be sufficient. Next is int boolean type, leading 0, and I think I have to count total how many unique integers now, or non-zero digits. So just non-zero digits. So int nz, nzd, non-zero digits, and one last, the constraint that we pass as s. Just have to keep track of this. So if this index, this is the base case, so we just return if this nz non-zero digits is less than equal to 3. So this is what we want to return. So if it is satisfied, so we will return 1, otherwise I will return 0. Automatically this is handled. Next is we will define the upper bound based on the type. So I think lower bound is just 0 and upper bound is based on the type. So type, if type is true, then s of idx minus 0 to convert it into integer, otherwise it can be 9. Now we will just use a for loop. I will start from the lower bound, I will go up to the upper bound. Right, and we can just define the result. Again, the answer is independent of number of zeros because we are counting non-zero digits and not 0 as digits. So LZ was not required, but we have done it anyways. So this simple result plus equal to this function I will call again. Now let's try to understand. So index will be incremented by 1. Tight is dependent on if I am already tight, and this I or the digit is upper bound. Next is leading 0. Leading 0 for the next is defined by if I'm already leading, and this I is 0. Next is non-zero digits. This is nzt up to this, plus if this I is not equal to 0, and then it goes as it is. You don't need this bracket because only one line. So first let's memoize it directly. So LLDP IDX, since it's 10 to the power 18, so 19 digits, 19 positions. Type 2, this is also 2. How many non-zero digits? Maximum 20, 19, I think 18. 10 to the power 18, so 19 digits, but 20 I require because it can be from 0 up to 19, so 20 positions, or yeah, in the array, that will be sufficient. and we will calculate the answer for. We will also require something called, let's take it LL, and so that we can do the -1 thingy. Okay, and let's say E1, or let's say R equal to this solve function being called 0, it is initially 1, so 1, nz is 0, and this is A to B, no? So B, and L M1, so L minus 1 basically. It's the same thing. So A minus 1. Before solving for the second one, I have to reset my dp function, or reset the dp. And in the end, we just want to print C out. This R minus L, followed by some new line character, LM1, I guess. Of course, we have to memoize this. If this dp of I believe this should work. Okay. You only got only 55 numbers. At most 3, no? let's see. Okay, it's not equal. No, this will not be the answer. Okay, I've made some small silly mistake. So here I wrote that return dp of this is not equal to -1, which is, I just copied the wrong thing. I mean, I wanted to calculate the answer. So you see it is passing. Yeah, I just, silly mistake. I think this will pass. Let's try to submit this. I think some round is going on, so that's why probably it will put some things in queue for some time, I guess. Okay, I think this will take some time. Okay, it is saying that it is running. Yeah, it is accepted. Actually, also me first time solving this problem. Okay, now let's go to the next problem. Let's see what next problem we have available. So we have a problem called number of beautiful integers in the range. Let's see if I can find this problem. So I think this is the problem. Okay, again, first time me solving this. So you are given positive integers, low, high and k. Number is beautiful if it meets both conditions. The count of the even digits in the number is equal to the number of odd digits in the number, and the number is divisible by k. Yeah, that last part is tough. That I can easily keep track of the number of even digits and the number of odd digits. But how will I keep track of the idea if the number is divisible by k or not? What is the maximum value of k? Up to 20. So I cannot keep track of the number. That is impossible. Low to high, we can just use the prefix sum idea. Funny thing is k is up to 20. Not some big number whose divisibility checking is tough. I just have to know that if it is divisible by k, Low and high must be very high. Yeah, 10 to the power 9. Ah, that's 10 digits, not an issue. Say I'm going digit by digit. How will I keep track of divisibility? Like in modulo. Let's discuss this problem on the next class. For now, I'm not getting any ideas how I can probably think about this. But I promise you I will get back to you on this with proper explanation and understanding, like I've done for the other problems today. Let's solve some other problem. Okay. Okay. So we will solve this problem. So we will try to solve this problem. This is called counting numbers. I have solved this problem before. So you are given 2 L and R, and I want to calculate the number of numbers such that none of the numbers have 2 digits adjacent to each other equal. So idea is that I will consider all the digits. I will go digit by digit, but I have to keep track of the previous digit. So basically the idea is that I will not put some digit which is equal to the previous digit. So I will basically continue that part while putting digit at every position. Let's try to solve this. Let's give VS Code. Yeah. So we have 2 ranges. I think it has to be long because it is up to 10 to the power 18. Okay, and let's try to write down the solve function now. Uh, Here in this problem, leading 0 will be required. Why? Because do we care about adjacent digits equal to 0 if I am in the leading 0 phase? No, because that will be allowed. 0 0 0 3 2 is a valid answer. So if leading 0 is 1, then we don't care if I am equal to my previous digit or not. Otherwise, I do care. So since we are just counting, we just return 1. While we will keep track of, we will only go up to the last by creating valid integers or valid things. Do I have something called modulo thingy? No. If leading 0 is true or leading 0 is not true and I is equal to previous digit, then we don't want to consider this at all. Otherwise, same logic for tight. Initially we can keep previous digit as -1, but that will be a problem in memoization. So we will make the previous digit as 11 or 10 because that is not a possible digit. IDX is up to 10 to the power 18, so 19 positions or 20 positions. 10 for 1 followed by 18 zeros. So 19, yeah, 0 up to 19. Previous digit can be, I'm considering 0 to 10, so 11 and nothing else. See, it's passing. Let's try to submit. Okay, let's try to choose some file. Will this be visible in the OBS? Here I've just submitted the file. Put on the file, and we'll just click on submit. It's saving some compile error. I think I made some mistake. I think I navigated to the wrong file. Yeah, this is correct, I guess. Sorry, I uploaded the wrong file. Yeah, as you can see that this is the code that we wrote. Yeah, it is accepted, and this is the code that we wrote. I hope this problem is clear. We will solve one more problem. This is a very interesting problem which I've never solved before, so that's what makes it interesting, I guess. Let's see. This is called Benny and the Broken Autometer. Let me just log in. Just give me a moment, I'm just actually logging in. Okay. Just give me one moment. Yeah, I've logged in. Let me just, yeah. Do I have dark mode for this? Let's go to the settings, or no. Let me just try to find out the dark mode. I cannot look for dark mode now. Let's try to read this problem. So one fine day, Binny decided to calculate the number of kilometers she traveled by bicycle. Therefore, she thought of an odometer and installed it on the. But the odometer was broken, and she was not able to display the digit 3. This precisely means that the odometer won't be able to display the numbers having one of their digits as 3. For example, after the number 1299, the odometer will show 400. So I want to calculate the real distance. So can I say that the number is actually the given number minus all the numbers, or how many numbers that have at least one of the digits as 3, because that number will be skipped, right? Yeah. So that is the idea. Do we have C++? No. Can I parse this? Yeah, I can parse this. Oh, not this. So let's go back to VS Code. So the idea is again the same. We'll be using the same idea as before. Here we will just be okay. Let's count out the number of digits that has the digits 3 in it. So we will use the same. What should I say? The digit db function. Similar. Of course, we will make a lot of changes. So and also we will have some test cases and all. So here we just have one integer n, and we want to know how many integers. Do I have? I think n minus 1 will work, or up to n, let's say. And we can just output that, I guess. Okay, but of course the logic will change. So number of 3's we want to know. So maybe n3. So we want to know if it has at least 1 3's. So n3 is greater than or equal to 1. Right? Now the logic for it will be n3 plus if I equal to 3. So this gives me the count of number of digits which has at least one of the digits as 3. Multiple can also be 3. Let's try to run this. Probably there is some mistake, but okay, failed. So the answer is I think n minus r. Because out of that, the ones with having at 3 will be skipped. I think this is passing. Let's try to submit this. First, let's compile and test the code. Of course, let's try to submit, I guess. Yeah, so sample test case is passed. Okay, I think it will take some time to evaluate the solution. But this is actually a very good problem, I think. Like, compared to the classic numbers that we solved on code forces, just one minor change. And I will say that most of the DGTP problems are like this only. Probably, I'm not sure, because I've only solved around 10 to 12 problems on this topic. But out of those problems that I have solved, I found that it's just about thinking how to formulate that in terms of digit, how to update the states and all. Also, I have never used the bottom-up approach where we just use loops. most of the times you see, if you multiply all of these states now, it will not cross even 500 or 600 or 1000. So that many, if I am doing memoization, I don't think I will get TLE. If I refresh this, submissions. Okay, result is saying that, yeah, it is accepted. I can probably memory and all, difference is nothing. This is my submission, and can I just put the dark mode or something? Okay. So only for the theme I think I'm allowed. Oh, okay, I guess this is passed. So this will be the last problem for today. Thank you very much for watching. Next day we will try to tackle some of the difficult problems of digit dynamic programming. That will be all for today, I think. Thank you very much for joining in. Have a great day. Goodbye.